This video is going to talk about the applications of exponential functions. So let's just look at a couple of different examples very quickly here. Number one, we've got this example where a math teacher is meeting with a pre-calculus parent, wants to explain what's happening to their child's grades, and they just happen to notice that the grade is going to decrease exponentially. Remember, an exponential function basically is a function where we're multiplying over and over again, right? Multiplying, because if we said something like 2 to the x, right? Well, every time x goes up by 1, we're multiplying by 2, and then times 2, and times 2. And that'd be doubling the grade. Well, we definitely notice that's not happening, right? But if we want to know if from grade to grade, right, to get from one grade to the next, what's happening to these functions? Well, 100 times something gives you 90. Well, if we think about it, 100 times something is going to give us 90. Why not just divide, right? Why not figure out what that is by division? And if you take a good look at it, 90 over 100 equals 0.9. And actually, if we check it out, you'll notice 81 divided by 90 and 72.9 divided by 81. All of those numbers actually come out to 0.9. So it's basically we're saying, well, 100 times 0.9, right, gave you 90, times another 0.9 gave you 81. If we multiply 72.9 by 0.9, you'll notice we'll very quickly get, right, let's move that out of the way, 65.61 or so. So again, the idea is, right, the grades are going down by 10%, right? We're 90% of what we used to be. We're 90% of what we used to be, but they're going down by 10%. So the idea of our exponential function is we're going to take our initial value, right, our 100, multiply it by 0.9, however many times it takes, right, to get from test 1 to 2 to 3 to 4, right? If x were sort of the number of the test, although we'd have to be a little bit careful here because we said that that was test 1, right, not test 0. So we might have to say a little -1 there. We plug in 1 for test 1, right? Then we get 100 times 0.9 to the 0 power. Well, that's just 100. But after that, it's going to multiply by 0.9 to the first and 0.9 to the second, 0.9 to the third. It's going to work from problem or from number to number as we work our way down. The idea of a exponential function, again, is that we have that base raised to a power that's getting multiplied over and over and over again. It's going to consistently either grow or decay. Now, a couple of different applications of exponential functions. We've got compound interest. Again, there's the regular compound interest, 1 plus, so 100% of what you already have, plus the interest rate. Now, the interest rate is often divided or occasionally divided by, right? It wouldn't have to be. You could definitely write a more basic function. The principal is the amount you start with, that initial value. And that actually goes across all exponential functions. I'm just going to make a little side note. Note the times the principal here, times the principal there. Down here for radioactive decay, we're going to multiply what we call the initial value. That number in front is our starting value, right? Our beginning value. But for a regular compound interest, I would take 100% of what I already have, right? Think if I already have money in the bank, I'm going to keep that money, right? So I would take 100% of that plus my interest rate, right? Times my principal, right? Notice the distributive property here, right? Principal times 1, principal times r. So we've got the principal, we're adding on the interest rate, and again, we're going to do that for a certain number of years. But compound interest often says, well, what if we're taking that monthly, right? N would be like saying monthly. Instead of years, we're going to take that 12 times a year, but I'm only going to get 1/12 of the interest, right? We might remember that. So again, that's the basic compound interest formula. If for any reason, instead of being monthly or daily, and we'll talk about a couple of those here in a second, we're talking about continuously compound interest, if for that's the reason, then we're going to switch over to this function over here, PE to the RT, the PERT formula, where notice the N has disappeared because we're continuously compounded interest. We're going to use that natural base E. We're going to raise that to the interest rate, and again, multiplied by the number of compoundings, or basically the number of years, T. Down here at the bottom is radioactive decay. You'll notice the major difference, and we'll come back to this one. Major difference is that this is a 1/2. Again, we're decaying away rather than growing, right? And we could have compound interest decaying, by the way, if we had a negative R value. If the rate was decaying, right? If you made R negative, it would decay away. But again, notice radioactive decay, 1/2 to the power of t over h. We'll talk more about that one in a second. Let's talk about compound interest first. So we have two good examples for you. Determine the balance A for $1,000. Note there's our principal, right? That's going to be P. Invested at a rate, right? 4.2%. Now remember, when we apply rates, we always put them in decimal form. So we're going to move that decimal 2 places, call that 0.0. Oops, bad move on my part there. 0.042. We got to move that decimal 2 spots, right? So 0.042. APR, annual percentage rate, so talking yearly for 30 years. But we're going to compound semi-annually, right? So there's that idea of that N. We're saying semi-annually twice a year. So I'm going to say I'm going to get half the interest halfway through the year, and then I'm going to get half that interest again at the end of the year, but building on my interest. So again, when I plug in my numbers, 1,000 times 1 plus 0.042 over 2, half the interest. But again, I'm going to get that interest 60 times over, right? Because I'm getting that for 30 years, twice a year. And again, if we just type that into our calculator, you'll notice we get $3,479.72. With the kind of the same ideas, $1,000 principal, 4.2%, 30 years. If we're talking continuously, again, that's where we're going to switch over to E. So we're going to plug that into our PERT formula, 1,000 times E to the 0.042 times 30. And again, notice we get slightly more money because, again, our interest builds on our own interest. The first interest we got in that semi-annual earned us a little extra interest the second time around. Well, if we're continuously earning interest on interest, we're going to get a little bit more money. Now, let's talk about that exponential decay function that we talked about, right? That carbon-14 is a great way to talk about half-lives, or basically exponential decay. Again, 1/2 to the power. So what does Q sub 0 or Q of 0 mean? Well, if t was 0, basically it means we're trying to find our initial amount, right, when t is 0. So let's plug in 0. Well, 0 divided by 5,730 will still be 0, right? 1/2 to the 0 is always 1, and 1 times 10, right? Essentially 10 times 1/2 to the 0 power is going to just be 10. So what that's telling us is we're going to start with 10 grams, right? 10 grams of carbon-14 here. Is this a growth or a decay function? Well, as we said, it's 1/2 to the power, so it's definitely going to be decay. 0.5 is less than 1. And as the years go along, what does t over 5730 mean? Well, instead of 1 year causing us to have half the amount, basically if we plugged in 5,730, this exponent would turn into a 1. So 10 would be cut in half after 5,730 years. Basically, 5,730 is the half-life, as we would call it. It takes that many years for exactly half of our amount to be gone. So let's look at a graph of it over 0 to 2,000 or 20,000. Remember, after about 5,730, so notice that's going to be right in this area here. We're right about that 5, right? Here was 5 on our graph. And again, we're going to be right there at about 5,000. After another 5,000 years, we're going to be at half of that, and add half of that, and half of that. So even after 20,000 years, right? Almost 4 half-lives, not quite. We're just short of about a quarter of our stuff there, right? That's almost 4 full half-lives. Almost a quarter, right? We're at a half here. We're at a quarter here. This would have been an eighth. This would have been a 16th, right? We're at almost a 16th of it. Notice it'll never disappear, though. It'll never disappear. Now, to find any particular value, it's easy enough just to plug in t. But notice down here at the bottom, approximate how many years. Find x, right? Or find t for us right now. That would leave us with just 4 grams. Well, we can approximate that, right? 4 grams is going to be, somewhere in this area. So I'm guessing somewhere between 5,000, right, and 10,000. But again, I don't know exactly where that is. And since we haven't really studied solving these equations for a while, the easiest way to do that is actually put that in my calculator, okay? We're going to put that into the calculator, and we're just going to use our intersect function. I'm going to graph a line at y equals 4. And again, if I press second calculate on my TI-84 calculator, if I can figure out where those two lines cross, well, they're going to intersect at, again, 7,000 574.648 approximately years. So again, the best way to solve these, since we haven't really talked about it yet, is just solve by graphing. Graph that horizontal line where we know we want y equal to 4 and figure out where our two lines cross. Again, second calculate using that trace function. You should be able to find an intersection point. If you have any questions on that, make sure you talk to your teacher. Otherwise, have a great day.